So we had 3 factors that we had to worry about. We should remember them. That was the temp, that was pressure, and lastly, those intramolecular forces. Those were the 3 factors that determine what state of matter my substance is in. Now, in my throwback to Unit 4, we talked about 3 intermolecular forces. Hydrogen bonding, London dispersion, dipole. Which one was the weakest of the 3? Not dipole. London. London was the weakest. Followed by what? Followed by dipole, and that means that my hydrogen bonding was the strongest. So, let's jump into what we're going to be doing today. Now, you're going to notice that on your piece of paper, I have a bunch of blank spaces for you. And that's for a reason, because I want you guys to actually be able to take your own notes. So, we're going to start off with pressure. And pressure is defined as the force applied over a unit area. Now, give me a quick second. I have to fight through all my stuff. Hello. This is Wiseman. Oh. Jesse for early dismissal. All right, Jesse's on his way. All right, light up. All right, Jesse, you're going to want to watch the notes for today, because here's the thing, is that in your notes, we actually draw out the phase diagram that you're going to be looking at. And we're also going to go through the boiling graphs that are on the back. So make sure you watch the videos to understand what's going on. Everybody else. So if I have this term that's defined by a force applied force area, we're going to see that my pressure is just my force over an area. Now, a big thing, I made a small mistake last time. I told you that 1 atmosphere equaled 14.2 pounds of pressure. Now, unfortunately, Mr. Wiseman made a small clerical error. It's not 0.2, it's 0.7 PSI. PSI standing for pounds per square inch. What we're going to talk about is that we're going to see that the higher the pressure, the more likely my substance is a solid. Why is that the case? Because the more pressure pushing down on something, more pressure means less room for molecules to move. The more pressure I put on a system, the less space the molecules have to move. Now, we are going to see an experiment of pressure firsthand. In a second. Because I do want to steer your attention to the front. Now, I'm not going to change the view of the camera, because I don't need to be going back and forth. You guys get to experience the oohs and the ahs in person. Now, I got a hot plate. I got some water in a can of Coke. And I'm heating up that water. Now, what's happening inside this Coke, if you can hear carefully, you can hear the water as it's boiling. It's popping. What ends up happening is that as the water becomes vapor, there's very little place for the water to go, for it to escape. So that means that my can is building up pressure. Now, in a hot environment, my pressure in my can builds up. But if I take my hot can and I present it to, I don't know, a cold situation, what I get, exactly, you guys get the oohs and the ahs. What I get is a violent equilibrium. We are going to talk about what makes a boiling point today, and it's all in reference to the atmospheric pressure. What happened is that my can had more pressure in it than the air around it. When I put it in a cold environment, that hot water quickly cooled down, meaning the pressure drops almost immediately. And as it drops, water's going to move into the can to take its place, crushing it in a second. We had a real life experience with this a couple years ago with the Ocean Gate fiasco, that privately owned submarine on its way to the Titanic, where the outside of the submarine had more pressure than the inside of the submarine. And much like my can imploding on itself, so did the submarine. Now, the thing is that this movement of water, this immediate change in pressure, happened faster for the people who were on that submarine than their brains could register what had happened to them. They died before they could even think about it. That's how instantaneous it was for them. Not exactly the great story that you want to write home about. What did you learn in school today? Well, I learned that those guys on that Ocean Gate thing that you died before they even knew what happened. You learned that in chemistry? Yeah. What do you think I was going to learn in chemistry today? I know. I'm getting better. I'm getting better. Let me change one of my students' grade. Time to fast. Should I put? There we go. There we go. All right. But what happened? As pressure built up in my can, when I changed pressure, I had an immediate response to it. That's what we're talking about when we're getting into pressure. I know, it's probably Carlos. Juan. All right. Oh, it's in there. All right. All right. So let's talk about atmospheric pressure. We talked about what pressure is overall. But we're going to break down our pressure into two big things: atmospheric pressure and also vapor pressure. What we saw was a great example of vapor pressure. But here's the thing, is that your body is constantly being bullied by the air around it. The definition of atmospheric pressure is the pressure from the weight of the air around you. Now, we usually mark that as our 14.7 psi. Now, I'm giving a very specific number for this. And I have a little note on myself, Mr. Wiseman, don't forget about the Megberg experiment. Because I want to show you how we know atmospheric pressure is all around us and it's constantly pushing us. To help me out in this experiment, I have a cylinder. Oh, not cylinder, I have a sphere. I'm going to make sure my sphere is tight. My hand up the seat, that's what's going to happen. And that's going to hit, someone's going to fly and hit themselves in the face. And it's not going to be a good situation. Tighten that down just a little bit more. All right. So, before I start plugging things into each other, I want to walk around with that. I want us to see that there are no screws, there's no threads in my container. It is just flat metal in my container, no ridges, nothing for them to grab onto each other and hold on to. This is very important for what we're about to do. No threads, no threads, no threads. Walking around, excuse me, there's here, no threads in my container. It is quite, stick together, and that's it. No threads, nothing to hold this thing together. Very important, very important, very important. Now, stop it. All right. Here's the thing. Right now, there's pressure. When I put this container together, there's air in my sphere. And that air pressure is pushing outwards on my container. And I have the pressure from the air around me pushing inwards on my container. Meaning, at the moment, I have a net zero of pressure in and out of my container. Therefore, I can take it apart pretty easy. If I remove the air from my container, that means I only have pressure pushing the container into itself. Of course you did. Okay. All right. I was going to make sure I pull out all the air I can. Stop it. There. Get it. Oh. Got a little bit. That's not good. Oh. I'll start plug things in. Alright, turn it on. Very hard for me to pull this apart. Now you might be going, well, Mr. Watson, clearly you're fighting a vacuum. What the hell did you expect is going to happen? No, congratulations for volunteering yourself. Because what we're going to do is we're going to take a little bit and see who is the strongest in the class. No has elected himself to be our first contender. First contender. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. All right, shut that down. All right, no, congratulations, sir. You are my first contender. Now, key thing on this one, we want to make sure that our elbows are in a place that if this thing does go flying out, you're not, boom, bouncing yourself into the cabinets, because that will hurt. No, you're gonna step in. We're gonna see how you go, buddy. Oh, come on. Oh, hey, the strong boy was able to pull it apart. Look at that. Was it as easy as just pulling it apart? No. Why? We can measure how much weight it was for us to pull that apart. Not the easiest thing to do. But thank you, sir, for volunteering yourself into our situation. By removing the air of my container, I just have the pressure pushing my cups together. Because I only had air going inwards. Now, let's do a couple other things. I don't know if you guys have heard about the situation in the Middle East, and there's a certain strait that's making everything more expensive every day that we wake up. So, here's the thing. We got to get creative. Now, people say, hey, man, you know what you should do? You should grow your own food. And I'm like, yeah, that's great and all, but, I don't have a green thumb to save my life. I have a couple spider plants in my house, and these things will not die. They are incredibly durable, and they can go months without any water and still bounce back pretty quickly. Now, what I hear is that there's somebody on some kind of weird podcast. Never trust a guy with a podcast. You never know what's going to happen. But they're saying, marshmallows are like the next superfood. All right. That if you put it in the right situation, that it'll grow by itself, which is insane, to be absolutely honest with you. How do I grow food just by putting something on, by doing something to it? But we're gonna see what they're talking about. Now, usually they're talking a bunch of trash. Now, to help me see how much my marshmallow may grow, I also have an extra marshmallow for reference. So, I crank out my stuff. Whoa, hey, look at that. Look at that. Hey, who knew, guys? I am an amazing chemist. I'm able to grow food without having to do anything. Who is that? Come on in, man. I have done magic. I've grown food without having to grow food. Now the thing is that, of course, we have to test it, see how it is, because you never know. Oh my God!
Are you okay?
What happened?
Oh no!
What happened? It's not supposed to look like this.
Solid? What?
It's supposed to look like this. Okay, so I can't grow my own food. That's fine. That's fine. You know what I can do? Everybody needs a side gig. I got the greatest idea. Here's the thing. I'm lazy. I don't like working, but I have an asthmatic brother, and I can force him to blow balloons for me. I keep getting the hell away from him until he blows up all the balloons. I can't breathe, man. I can't breathe. Blow the balloons, boy! He complains all the time. I gotta find another way around this. All right, so if the marshmallow grew, the balloon has to fill itself at this point. All right, fingers crossed. Oh. Hey! Look at this, guys. I'm back in business. All right. Now, here's the trick. Now, obviously, I get the balloon out. I'm going to be a hit at all these birthday parties. I don't even need that asthmatic dude. I can get the job done by myself. God damn it! No! Why did it shrink? What did I take away? I took away the pressure. Because I took away the pressure, I allowed the molecules that were in my container to expand. They didn't have to push against anything. They were able to push out. The moment that I broke the seal was the moment I reintroduced the air back into the system and returned pressure back to where it was. A cup of water. Yeah, it's water. Here's the thing. What we're going to see here, guys, is that as I remove the air around it, there is no hot plate, there's no nothing in here other than just the water. By removing the air around it, I'm going to lower the boiling point of my water. Because what we are going to see today is that my boiling point, for things to go from my liquid to gas phase, my vapor pressure, the pressure of of my container above my liquid has to equal atmospheric pressure. Once I hit this point, I hit my boiling point. So as I pull all the air out again, takes a little bit. Oh, uh-oh. Uh-oh. My hands are off it. I'm not touching it. But it's starting to boil. I think I'm covering a bit of the lid of the container of the lid. There's enough time. Oh, no, let's start. This is not catching as well as I thought it would. Probably best to conceal the replay. Give me a quick second. I think that's probably what happened if I don't have a great. There we go. Check the base of this real fast. Yep, that's what happened. It wasn't all there very well. Come on, nothing like that. Okay, on you go. As I keep pulling air out of my situation, eventually my water will start to boil. Again, because by lowering the pressure of my system, it lowers the temperature that my water needs to boil at. We're going to see that when we hit our phase diagram in a second. Well, this one not as excited. I hope that the vacuum isn't dying on me. Good. I'm about to take this back down. Yep. Alright, so unfortunately, my oil is a little leaky, so it means that it's not working as well as I want it to. But by lowering the pressure, I lower the temperature my water needs to boil. Still as cold as it was before.
So you say you lower the what?
I lower the pressure around my container, and that lowers the temperature it needs for water to start boiling.
Does that mean like instead of like let's say 100 degrees, it's gonna drop to like 50 degrees instead?
Well, it started boiling at room temperature.
Oh.
Man, in a second. So I want to get people stirred up, and I want you guys to be looking at the next question. Oh. Okay. So, we had a little bit of fun. We acted a little crazy. A little goofy is what we were doing. Therefore, it's only fair that we do a little bit of math to go along with it. I know how much y'all like doing the maths. Make sure that's what you need. Everyone needs themselves a calculator. Without a calculator, we're going to have a little bit of issues today. On the back of the second page. You'll see I have several equalities at the top of your page. Oh, I meant to talk about those real fast before we got that far. Give me one quick second. I want to tell you what all those items were. I meant to do that. I do apologize. I was too busy upset about the vacuum not working as well as it should. Wait a second. All right. Nope, that's blank paper. Of course, the very thing that I need is somewhere hidden in front of me. For sure. No. All right. Before we get into the other stuff, I do want to point these out. So, ladies and gentlemen, I will not ask you on a test, where do I use atmospheres or pKa's or torrs, but you may want to know where they come from. So, ATM is not your parents. Anyone know what ATM stands for? If I'm at the bank and I go to an ATM, you know what it stands for? Automatic teller machine. ATM. Here, ATM stands for atmospheres. It is the more commonly used measurement for pressure. Guys, pKa stands for kilo pascals. Now, when do I need to measure kilopascals? Is that's what I'm using for sub-atmospheric conditions. Also, if you go into HVAC or you family in HVAC, you also see that with AC units, measuring very small material. mmHg, that is millimeters of mercury. One of the oldest ways for us to measure atmospheric forces is mmHg. Torr is used for, excuse me, atmospheric pressures. You saw these in earth science as the isobars. We're talking about pressure in the atmosphere. The bands of similar pressure. They're also used in high-powered vacuums. In PSI, we know this one is pounds per square inch. Now, we present you with these so you guys know the different types of ways we can measure pressure. Now, when you flip your paper over, you're presented with 4 questions. Convert the following pressure units. Use the pressure equality below to complete. Show all conversion work. We're going to do 2 together. I'm going to do 1. You're going to help me out with 2, and I'm going to have you do the other 2 by yourself. So, my first question is I need to convert 1.50 atmospheres to kilopascals. So, like anything, I'm going to use my differential analysis in order to get this done, right? Those equality fractions. It's the easiest thing that we did. 1.50 ATM, because remember, ATM stands for atmosphere. I want kilopascals, KPA, and I want to get rid of atmospheres. I go back, I take a look at my equalities. I see that, hey, 1 atmosphere is equal to 101.3 kilopascals. So, 1 atmosphere under 101.3. Here's where I need my calculator. If I do a little bit of math here, I'm going to get an unrounded answer of 151.95 and a bunch of other stuff that I don't care about. How many sig figs can my final answer have? 2 or 3? 3, because the 0 is tailing, but there's a decimal place.
How you doing today, sir?
Pretty good.
Could I get your side just for a little bit? I'm sorry to distract your classroom. The college coaches want to talk to him real quick.
Who do we want to talk to?
Shepherd University. They just want to talk to him. They just want to see him. Okay.
Oh, do you want to talk to Josiah for a quick second?
Yeah.
Oh, that's fine. That's fine.
Okay. Appreciate it.
No problem. All right, guys. So, is my 9 big enough to push my 1 to a 2?
Yes.
Absolutely.
What happened?
I thought he wanted Shepherd University to talk to all y'all. I was like, I didn't know y'all were athletic. Oh, damn. All right. So, my rounded answer can't be more precise than my question started, ma'am.
How did you get the 101?
My equalities.
Oh.
Right here are my equalities, right? So that's what I'm going to use. So, let me get you guys help answering This question, talking about a can of compressed air, has a pressure of 2,800 millimeters of mercury. What would the pressure be in atmospheres? So, I rewrite my question. 2800 mmHg. I got my quality fraction. What it's going to be in my numerator? Millimeters mercury or atmospheres? Atmospheres. What's going to be my denominator? Millimeters mercury. So I go back to my qualities, right? In my qualities, how many atmospheres am I going to work with? 1. How many millimeters of mercury exist in one atmosphere? 760. So I sit there and I do the math. I'm going to get unrounded answer of 3.68, blah, 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 blah. A bunch of stuff I don't need. How many sig figs does my final answer have? 2. 1, 2. Is there 8 big enough to push my 6 to a 7?
Yeah.
Heck yeah, it is. 3.7 ATM. So I want you to answer 1 and 2 on your own. 95.0 kPa in the atmospheres, and then we have a word question. I want you to balance that out. While I get a little bit of tape and try to see if I can tape that oil down again. Where's my tape at? Okay. Yes.
Can I go after her?
That's fine.
Can I go after Nick?
Sure. Guys, don't be giggling and laughing. Make sure you're answering your questions. Because in a little bit, we get to do what every high schooler wants to do all the time. And draw.
What?
You guys are going to be drawing soon. They'll be drawing.
What are we drawing?
You're going to draw, guys.
What the?
You're going to draw. You're going to draw some wax.
What?
You're going to draw some wax.
Crap.
Wax. Draw some wax. Wax. You guys know I draw wax. That's the best job in the world, to subject people to my different voices.
I would never say this. I would never say
Olivia, the numbers can't be stupid. They don't have feelings.
Oh, okay.
You don't have to be.
You know, the numbers, nah. The numbers don't have feelings.
Yeah, so what you want is, if you don't want to try. Do you need to cancel? Yeah.
How do you divide it?
Look at the equalities up top.
Yeah.
You're always just using the equalities up top. Yep, those at the very top of your page, so they're in both. You don't know.
So the one. Yeah.
Oh,
Proof earlier?
okay, thank you.
Oh, Cindy. Yeah, send her on down. Thank you. I know. All right, Cindy, you out of here.
Okay, thank you.
All right. So, Cindy, make sure you work on the homework. All right, guys, let's talk about it. So, ladies and gentlemen, I know we're having a goofy time in chemistry because we get to do goofy things today. But you have to bring it in every once in a while. So, I got 95 kilopascals. I need to figure out how many atmospheres that is. 95.0 kPa. Now, I'm going to use these equalities up top to answer my questions, right? Now, I want atmospheres. I want to get rid of kilopascals. So looking at my qualities, I see that 1 atmosphere equals 101.3 kilopascals. I do my math. 95 times 1 is going to be 95. Divide that by 101.3. I'm going to get some long number, 0.93780, blah, 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 a bunch of stuff I don't care about. How many sig figs can my final answer have? 3. So am I going to draw my rounding line between the 3 or the 7? That's a 7, because my leading 0 does not count. Is the 8 big enough to push my 7 to an 8? Yeah. Absolutely. So 0.938 atmosphere. My next question, 750 torr, guys, would be a reasonable atmospheric pressure when a low pressure front is going through. What would this pressure be measured in kilopascals? 750 torr is what I have. I want kilopascals. I want to get rid of torr. I go back to my qualities. 760 torr is equal to 101.3 kilopascals. 101.3 over 760. Now, when I do that math, I'm going to get a final answer of 99.96 and a bunch of stuff I don't care about. How many sig figs can my final answer have? 3? 2. Tailing zeros don't count without a decimal, right? Is a 9 big enough to push my 9 to a 10? It is. So my final answer is going to be 100 kilopascals, or another way to read this, if I use scientific way, 1.0 times 10 to the power of 2 kilopascals. Because now I see my 2 sig figs. Either one would be right. I'd recommend doing the scientific notation. All right, let's keep this going, guys. Now, like I said, we get to do what every high school student loves to do. We get to draw. So, ladies and gentlemen, every phase diagram, we're going to draw what the average phase diagram looks like. Now, here's the thing. Not, no.
I didn't say, I didn't before.
Not every phase diagram is going to look the exact same, but the steps are going to be the same. I'm going to see, we're going to make a graph. My y-axis, my independent variable, is always going to be my pressure. Usually it's going to be written in atmospheres, but not always, but usually. My x-axis, my dependent variable, is always going to be temperature. And that's usually going to be written in degrees Celsius. Now, my graph, my diagram, is going to kind of look like a messed up Y. There are two important points in my diagram. My first one is my triple point. My other one is my critical point. And they might be important because clearly we're going to put some definitions to them. Now, the coordinates of my diagram are always going to be the same. My top left coordinate, this area right here, will always be where my substance is a solid. Lower temperature, high pressure. The V of my messed up Y is where I'm going to find the pressure and temperature for my liquid of the sample, of the substance. What do I think the bottom part is going to be? This area right here. Gas. We can also use this graph to identify where we see our phase changes. If I'm going from a solid to a liquid, if I'm dealing with water, what's that change called?
Freezing.
Freezing. No, solid to liquid. Not freezing. Solid to liquid. Melting. If I go the opposite way, liquid to a solid, I stick the ice cubes in the freezer, they will freeze. If my liquid becomes a gas, what do we call that process? Evaporation. Evaporation. What do we call it when my gas becomes a liquid again? Starts with a C. Condensation. I hope you did. We talked about it in biology last year. Earth science too. You don't get a breeze on this one. If I go from a solid straight to a gas, what do we call that? Start with an S. Sublimation. And if I'm going from a gas to a solid, deposition. So, we have two terms that we have to identify from our chart. Triple point, critical point. The triple point is where all three phases of matter coexist. My substance is constantly jumping back between liquid, solid, gas at this triple point. All three states of matter are existing at the same time at the triple point. This is a very specific temperature and pressure. Coexist. They all happen at the same time. We're talking about something that's incredibly specific.
Curve is thick, right? Does that mean curve? What does it mean?
Coexist. It means they happen all at the same time.
Like, does it mean like this, where like there's solid, liquid, and gas? Like,
At the same time, yes.
how does that?
Because we're at the point where temperature is just right, that the molecules are interacting with each other, and depending on what their average kinetic energy is, they're jumping through these different states. No one's staying in one state right now. All three are happening at the same time. A little bit more pressure, we jump into a liquid. A little less temperature, we go back into a solid. A little more temperature, it becomes more of a gas. It's a weird theoretical place where all three stages of matter exist at the same time.
How it looks like.
Critical point, all the way at the top here. Beyond this point, liquid and gas become indistinguishable. What does that mean? I cannot tell them apart. Hi, Nick. So, my triple point is this weird place where my substance is experiencing all states of matter. My critical point, beyond this point, I cannot separate my liquids from my gas. With enough pressure and enough temperature, it gets very weird very quickly. Now, a lot of times when we start talking about critical points is that we're talking about like stars or planets. We're not talking about if I heat carbon up 100 degrees Celsius, does it get to a point where I can't tell gas from liquid? We're talking about incredible temperatures and pressures happening at the same time. Does anyone still need this up, or am I good to move forward? What was that? All right, I'm going to move forward then. So, vapor pressure and boiling point. We're going to see that vapor pressure and boiling point are directly linked to each other. Vapor pressure is the pressure exerted by a vapor above its liquid in a closed container. We saw with the Coke can, we had a little bit of water. Now we know, because temperature is a normal distribution, no matter at what stage, I always have some water molecules that are moving fast enough that they can escape into the gas phase. So they're already flying out of the liquids and into the gas, into the container. When I introduced heat to my water, I am pushing more water out of the liquid phase into the gas phase. The water vapor then bounces off the container walls and back in, increasing the pressure in the space above the can. Higher temps equal higher vapor pressure. Why? Because as higher temps heat my container, it causes my molecules to move faster. Which then creates more evaporation. Which creates more vapor pressure. The boiling point of a substance is the temperature in which the vapor pressure equals the atmospheric pressure of the liquid. What we are going to assume going forward in chemistry right now is ideal conditions. An ideal or normal boiling point is going to happen at 1 atmosphere pressure. Unless I say otherwise, we are going to assume the boiling point is at 1 atmosphere of pressure. Because that is where the vapor pressure equals the atmospheric pressure.
Listen, like, hey, can I leave the class because I need to go do something?
Don't say too loud because we're recording. But yeah, no, you're fine.
Yeah.
All right, we ready to move forward, guys? I'm also recording this so you guys can also see it later too. I give another 30 seconds. I'm gonna move forward. So I got 2 more things I gotta focus on before anyone starts heading out of here. All right. I'll move forward. Now, we're going to use this graph here that you have on your handout as well to answer these questions. Don't worry, we're practicing our graph reading. So we have 3 compounds. We have diethyl ether, which if we want to draw that out, H5, C2O, C2H5. Ethyl alcohol, it's just ethanol, which is C2H5OH. And then water, we all know that as H2O. Now, on my x-axis, my y-axis, I see my pressure. I have vapor pressure in torr, and I have temperature on my x-axis. If I were to ask what is the boiling point of diethyl ether, ethyl alcohol, and water at 1 atmospheric pressure, how can I go about answering that question? How many torrs fit into 1 atmosphere? 760 torr is equal. 760 torr is equal to 1 atmosphere. So, though it's kind of hard for me to see, I can just draw an imaginary line from where I think 760 is across my graph. Doesn't have to be perfect, but I can envision where that 760 torr line is. And then all I gotta do is see where my graph hits my line and go down to my x-axis. So if I'm looking at diethyl ether, if I draw a line down, what temperature does it look like diethyl ether begins to boil? 30 something. We'll say anywhere between 30 to 35 degrees Celsius. Ethyl alcohol, what does that look like it starts boiling? Like 80. We'll say something around 80. What about water? What's water's boiling point based off my line? 100. Okay. So I did make a mistake when I was writing this out. It should not ask what is the vapor pressure of diethyl ether at 400 torr, because that is the vapor pressure. It's supposed to say what is the temperature of diethyl ether at 400 torr. What do you think? Diethyl ether is that first line right here. What do I think the temperature is at 400 torr? Was it? 20, yeah. Because I'm asked about 400 torr. Draw that line down. Looks like it's 20 degrees, right? Here's an important question for you. Out of the 3, diethyl ether, ethyl alcohol, and water, who has the strongest IMFs? Intramolecular forces. Do I think it's the ether, the alcohol, or the water? Why? Because that's the highest boiling point, right? So my water has my highest IMF. Which one has my weakest? The ether. There's a reason for this. I'm good to go. Do you need a pass or? zero. Right, just make sure you do your homework, right? This page, front and back. Okay. Okay. All right. So there's a reason why this is happening, ladies and gentlemen. And I want you to flip your papers over so you can write it down. Because it's going to make so much sense when we take a look at it. So much sense. You're going to be like, wow, Mr. Wiseman, that makes total sense. If something has high intramolecular forces, that means that those molecules are sticking together really hard. If they're sticking close to each other, that means that there's less evaporation that's happening. Less evaporation, that means I have less vapor pressure. Because remember, I hit boiling point with my vapor pressure. The air above my liquid is equal to 1 atmosphere. So that means in order to get it to a boil, to enter the gas phase, I have to increase the energy, and all heat is just energy. So, the higher my IMFs, the more my molecules want to stick to each other. The more they stick to each other, the less evaporation that happens. The less evaporation that happens, the less amount of my molecules are making it into the air above my liquid. In order to get to that point, I need to put more energy into the system. Heat is nothing but energy. The more energy I put into it, the higher my boiling point is. The higher the IMF, the higher the boiling point. The higher the IMF, the more likely it's a solid. The weaker the IMFs, the lower the boiling point. The weaker the IMFs, the more likely I'm a gas.
Hey, Mr. Wiseman,
Yo!
did you change my phone?
I believe I did, but I'll check it again in a second. Keith, I want you guys to know. This piece of paper right here. Phase and vapor worksheet, front and back. Get your homework. I'm looking for both the front and the back.
Oh my head. Oh my head.
Make sure you're doing both sides. And with that, ladies and gentlemen, I'm going to pause on the recording, and we are good to go.